Yeah, sorry for the technical difficulties. Yeah, I'll try to check my email just in case people email me and say that they are having problems. So I apologize in advance for that. Great. Okay, so today we're gonna prove that homotopy groups of maps into an Eilenberg-MacLane space give you cohomology of the space. And yeah, we'll begin by reviewing the universal coefficient theorem, which many of you know. And did Ralph cover it last semester? Any? I forget.
Yeah, he did. He did cover it.
Okay, he did cover it. Okay, yeah. So we'll review that. Then we'll talk about like fibrations and mapping spaces, and then we use this to prove Eilenberg-MacLane spaces are unique. And then, time permitting, we'll talk about cohomology operations. I feel like there are a lot of material today, but there's only 20 slides. So yeah, so probably each slide has more stuff than usual. So definitely try to slow me down. I also, yeah, well, hopefully Skype works. Great. Okay, so what we're, first statement we're trying to prove is that, for A in a abelian group and X is CW complex, pi 0 of the space of maps from X into the Eilenberg-MacLane space is just the cohomology. And this version will basically immediately apply the version where you plug in pi I and then you'll get an n minus I here. People can see my cursor, is that correct? Or no?
Yes, yeah.
Okay, great. Yeah, my theory is that all of these things are the same. Zoom is probably supposed to be the best. We got an email saying to use WebEx. Okay. Yeah, and so there's there's a relative version where you plug in maps from a pair into Eilenberg-MacLane space rel base point, and then you just get the homology of X rel Y with coefficients in A. And yes, if you plug in Y as a point, then this is just a base mapping space. And if you want, you can identify this with reduced homology. So yeah. If you pick a point in a space, there's a natural isomorphism from the homology of the space, rel that point to reduced homology. Okay, so yeah, so let's just sort of see what this theorem says in an example. So when X is a sphere, an M sphere, and Y is a point, well, this mapping space is maps from a, base maps from a sphere into an Eilenberg-MacLane space. So base maps from a sphere is exactly homotopy groups, and the homotopy groups of Eilenberg-MacLane space is exactly A in when M equals N and 0 otherwise. And so this theorem says that this homotopy groups, or pi 0 of this space is supposed to be homology, and this is exactly the homology of a sphere rel base point, or if you prefer, the reduced homology. Okay, any questions? Also, I don't know how chat works on Skype when I'm screen sharing, so if I miss something in chat, someone should just yell at me, and also feel free to just interrupt and yell, but because I'll definitely, or hopefully I'll hear that. Any questions? Okay, yeah, so this is what the first thing we're trying to prove today. So yeah, so I guess to tell you what, this is we don't want just sort of an abstract isomorphism. we want an explicit isomorphism, and to describe what the explicit isomorphism is, I need to first remind you about universal coefficients. So yeah, I guess to state universal coefficients, I need these X groups, and you know, I'm not going to define them, but I'm just gonna. We don't actually need that many properties of them, but you know, they're functors from you know, it's a X. If you fix a ring R and a non-negative integer I, the X groups are functors in two variables, so it's contravariant in the first variable, covariant in the second variable. There's a 20% chance I got that flipped with the following properties. So when I is 0, it's just the homomorphisms from M to N. They are R-module homomorphisms. Yeah, so it takes in two R modules and outputs abelian groups. You know, the next property is that if M is free, then the higher X groups are 0. You know, above, you know, in positive degrees. Yeah, so let me see. I think that's correct. Wait. Yeah, so it's, I guess, if M is projective or N is injective. If I flip that, someone should tell me. Yeah, and if R is a PID, then the X groups vanish above degree 1. Yeah, and so the case we're most interested in is R is Z, and Z is a PID. And so if M is, you know, modules over Z modules are the same thing as abelian groups. So if M is a finitely generated abelian group, then this X group is just the torsion submodule of M. Okay. Any questions? I mean, if people want, or at some point I might have like a lecture where I sort of quickly review extant Tor, talk about group homology. I don't think we need that now. I think we can black box this, but yeah, are there any questions? And yeah. Okay. So the statement of the universal coefficient theorem says there's a long exact sequence, or sorry, short exact sequence, and it's split. So meaning this is isomorphic to the direct sum of the left and the right. It's not canonically split, but it is split. That says that, yeah. So you know, I guess what's the point of this exact sequence? We're trying to compute the cohomology with coefficients of A in terms of the homology. And to first approximation, cohomology is just the linear dual of homology, and then it says there's an error term. And you know, in general, if you replace Z with a more complicated ring, you don't just get a short exact sequence, but you get what's called the spectral sequence involving the higher X groups. But you know, this is just sort of a way of saying that the cohomology is completely determined by the homology, and there's an analogous short exact sequence the other way, showing that homology determines cohomology. And the corollary, if you plug in A is Z, and you assume that all the homology groups are finitely generated, well then, you know, structure theorem of finitely generated abelian groups says that abelian groups are just a direct sum of a free part and torsion part. Well, you know, in that case, then the cohomology is just isomorphic to the free part plus the torsion part, but the torsion part gets shifted. If anyone wants to tell me I shifted the torsion part in the wrong direction, you know, I would believe you. I think it's the right direction. I don't know. Yeah. So you know, this theorem obviously, you know, does not make sense, as stated, if you don't assume the homology is finitely generated, because, you know, they're like the rational numbers are in a abelian group, and it's torsion free, but the rational numbers aren't free. You can't find a basis. You know, you can't find a z basis for the rational numbers. You know, because you know, if it were free abelian, non-zero free abelian groups have elements that are not multiples of other elements, and that's not true for the rational numbers. Okay. Yeah. So this sort of concretely says, in the case of integral homology and cohomology, when everything's finally generated, there's a simple formula for going from between the cohomology and the homology. Any questions? So yeah, so since the you know, by Hurevich, the homology of Eilenberg-MacLane spaces vanishes below degree n. So universal coefficients says that that the nth cohomology is just hom from the integral homology into A. And so we're going to use this isomorphism to construct a canonical class in the cohomology of Eilenberg-MacLane spaces called the fundamental class. We denote by alpha. So alpha is so it's going to be in this cohomology group, which we've said is just isomorphic to hom in the category of abelian groups from homology into A. So we need a map from here to here. Well, I'm going to actually construct a map from here to here, but it'll be an isomorphism, so you can just take the inverse. So, you know, pi n of the Eilenberg-MacLane space is exactly A. Yeah, and then there's a Hurevich map like this. And because the lower homotypy groups vanish, this Hurevich map is an isomorphism. So you can take the inverse, so that gives you a map from here to here. Well, that map is exactly an element of here, so we get this class alpha here. Should I repeat anything about the construction of the fundamental class of Eilenberg-MacLane spaces? Yeah, so in one warning, the fundamental class is also a term associated with manifolds, and I don't think these classes are directly related. They're just sort of both important homology / cohomology classes. Okay, so now, so we're trying to prove that pi 0 of this mapping space is isomorphic to this cohomology group. Well, so the fundamental class lets us build the map that will be the isomorphism. So an element here is a function. An element here is a map from X into the Eilenberg-MacLane space. So what do? We send a function to the pullback of the cohomology class. So we have a map from A to X. We have a cohomology class in X. Just pull it back to a cohomology class in, you know, we have this preferred cohomology, sorry. We have this preferred cohomology class here, which is the fundamental class. And then just pull it back to cohomology here. I guess I dropped the coefficients in A. Okay, so this gives us a way of associating maps, cohomology classes, and you know, the claim is that this is the map that in fact induces the isomorphism. Okay, any questions? Yeah, so I'm going to prove the theorem. So for concreteness, I'm going to just prove it in the case that X is a torus, but hopefully you get the general idea. If you don't, speak up. So yeah, we're trying to prove, yeah, we're trying to prove like this theorem, or maybe we're trying to prove this more general theorem. I'm going to prove this more general theorem, but in the case that y is a point. So equivalently, we're going to prove it for reduced cohomology and based mapping spaces. Oops, where are we? Yeah, so we're going to prove it when x is a torus and y is a point, but I don't know. Yeah, and so we're going to, since y is a point, we're going to view it as, I guess this should say cohomology. We're going to prove a version for reduced cohomology, and then base mapping spaces, because that's what maps out of y are. So I'm going to suppress y from the notation. I'm also going to suppress a from the notation. So if I write cohomology, I mean cohomology in a. Yeah, so what's the idea? So we know the theorem for spheres. That was the first example. The theorem for spheres is basically just the definition of Eilenberg-MacLane spaces that, they have cohomology in degree A, or they have homotopy groups in degree n and 0 otherwise. So we know the theorem is true for spheres. And then what we're going to do is we're going to say, okay, I can build the torus out of 2 circles and 1 2-sphere. And then what do we need to do? Well, we need to say, well, if the theorem is true for a circle and a 2-sphere, then it's going to be true for a torus because we can build the torus out of these spheres. And then, there's nothing special about a torus. Any CW complex can be, built out of spheres in this way. Okay, so, we're going, so the one skeleton of a torus is S1 wedge S1. It's a figure 8. So we're going to prove the theorem first for the one skeleton and then for the entire torus. So we need to understand like maps out of a wedge. So based maps out of a wedge, it's exactly maps from each factor. So if you have maps from x1 wedge x2 into z, that's exactly maps from x1 into z cross maps from x2 into z if we're dealing with based maps. Yeah. Any questions? Okay. So now, if we apply this in the torus case, so we're maps from S1 wedge S1 is just maps. Well, base maps out of S1 is the same thing as loop space. So we get 2 copies of the loop space of Eilenberg-MacLane space. So maps from S1 wedge S1 is just loops of the codomain squared. So that tells us that pi 0 of this mapping space is exactly reduced homology so pi 0 of this mapping space is the same thing as, I guess I don't know how to annotate because I'm in Skype. Yeah, so I guess pi 0 of this is the same thing as pi 0 of this. So, but pi 0 of a product is just a product of pi 0 of homotopy groups commute with products. So pi 0 of this is pi 0 of loops Eilenberg-MacLane space squared, where the squared is on the outside. So, and then pi 0 of a loop space is just pi 1. So we just get pi 1 of the Eilenberg-MacLane space squared, which is just, I guess, a plus a when n is 1. And otherwise, the fundamental group of the Eilenberg-MacLane space is trivial. Yeah. Any questions so far?
Yeah, could you repeat that? You do pi 0 of that loop space.
Yeah. So first, let's ignore the squared part. Oh, maybe I can type. No. Oops, no, I can highlight text. Okay. That's not that useful. Okay, so it seems Skype is worse. Sorry. Yeah, so let's repeat this. So, yeah, so we're taking pi0 of this loop space squared. So pi0 of a loop space is the same thing as the fundamental group.
Yep.
Okay, and then the fundamental group of KAN is A when n is 1 and 0 otherwise.
Yep.
So, and then there's the squared term. So we've computed that the left-hand side is A plus A if n is 1 and 0 otherwise.
Okay, so like square behaves like super nicely with taking pi0.
Yeah, squares are nice with taking any homotopy groups, not just pi0. Yeah, so I think that's the argument that the left-hand side is isomorphic to this group here, and then that the middle is isomorphic is you know, I think more elementary. Like this is 572 topic. Like what's the reduced homology of this? So we see that both of these are abstractly isomorphic to each other, and then if you're a little bit careful, you can see that the map is in fact the map that we picked out is in fact an iso.
Okay. Okay.
Yeah, so it's just like maps out of a wedge of spheres is a product of maps from spheres. So like before we just knew the theorem for spheres, and now I'm saying we know the theorem for wedges of spheres.
Okay, right. Okay, I get it. Thanks.
Yeah, so we're just building up like the collection of spaces that we know the theorem for. Also, I think someone started talking, but like their internet was bad or something. So if someone has some question, they should repeat it. Okay, or I don't know. Or maybe when you were talking, just like there was some weird noise in the background that I thought was someone else asking a question. I don't know. Okay, yeah, any other questions? So, you know, this slide is saying basically, now we know the theorem for wedges of spheres. Okay, so it's gonna, you know, gonna be slightly harder to go from a wedge of spheres to the torus case. So we need this this lemma. So it says that if y is a sub CW complex of x and maps from y to q is connected, then we have a restriction map. Like if you have a map from x to q and y is a subcomplex of x, you can restrict and get a map from y to q. So the claim is that this restriction map is a fibration, and fibers are equivalent to maps from the pair xy into q rel base point. Which is exactly the same thing as based maps from the quotient. So this lemma tells you how to compare maps from x to maps from y and maps from x mod y. Yeah, so I guess a few comments. So if you look at the fiber over the constant map with value q here, or value q naught is just some point in q, then you exactly get maps from x into q that send y to the base point. You know, in general, what is the fiber? Well, you have this, you pick your favorite map from y to q, and then it's maps from x into q that on y agree with your chosen map over here. Yeah, any questions on the statement of this theorem? Yeah, so there's, I guess, relative and based versions of the above theorem. You know, I guess like it would involve at least 4 spaces and lots of parentheses. So if I were to write it down, I think it would be intimidating. But if you were to try to guess, what the relative version of this theorem was, you would presumably guess correctly eventually. If you were to guess and then think about it, you would come up with the correct answer. Yeah, and also, you might say, like, it's a little bit of weird, this assumption that maps from Y into Q is connected. Yeah, so without that assumption, it's going to be a fibration if you restrict to a given path component of this mapping space, but it could, the fibers could depend on what path component you're in. Yeah, and I guess everyone can hear my dog barking at the garbage truck, probably. Yeah, are there any questions? I'm gonna go grab my dog, sorry. Sorry about that. Okay. Yeah. Okay, so what are we, how are we going to use this to study the torus? Well, the torus mod S1 wedge S1. So if you think of the torus as like a square, then S1, you think of S1 wedge S1 as the boundary of the square. You think of a torus as a square with sides identified, then this is the boundary of the square. And the quotient is just the square mod boundary, which is S2. Yeah, so was I right? Oh yeah, so yeah, so I guess like maps from the torus rel this one skeleton, this figure 8 one skeleton, is the same thing as base maps from the quotient, which is base maps out of S2. Yeah, so I guess this slide just lists a bunch of facts that we're going to use on the next slide. The next observation is if you loop an Eilenberg-MacLane space, it it shifts homotopy group. So the loop of a KAN is a KAN-1. And then the next observation is we're going to need to know what pi1 of this mapping space is. Well, pi1 of maps from X into an Eilenberg-MacLane space is just pi0 of loops for maps of X into an Eilenberg-MacLane space. And then loops commutes with mapping spaces. So like loops of maps from X into something is the same thing as maps from X into loops of something. That's just like oh, I guess here everything is based maps. Sorry, I should have written based everywhere down here. This is, so like this equality, this being equal to that is just like some usual adjointness property. And then the last equality is just if you loop an Eilenberg-MacLane space, it shifts, you get an Eilenberg-MacLane space the lower degree. Yeah, so it says that pi1 of maps from an base maps from X into an Eilenberg-MacLane space is the same thing as pi0. Actually, this might be true without base maps also. Into the same thing as pi0 into an Eilenberg-MacLane space of lower degree.